Okay, let's get started. So today we will first talk about the background knowledge. Then we will talk about buffer overflow. So today we will only do the local variables buffer overflow. Next week we'll talk about return overflow, the return address, and everything else. Oops, no, sorry, not this one. Should we? So we talked about system call last week. We finished the system call, I believe. Okay, we're going to talk about piping. So piping is a feature in Linux and use these like systems. We are going to use some basic piping techniques in this class. So we're not going to talk about the very advanced techniques, only just what we're going to use in the class, right? So every Linux process has three initial channels of communication. It's called a standard in, standard out, and the standard errors. So every process, when it is created, there are already three file descriptors created, connecting to those three communication channels. So for a terminal application, those three communication channels actually are connected to the same thing. It is the terminal you are saying it. But there are three different file descriptors from 0 to 1, 0, 1, and 2. So std in, standard input, obviously is where your share use this to read commands. Your program basically read read data from standard in. Then your program can also output data to the standard out, or it can also output to standard error. Okay. So if you want to redirect the output to somewhere else, you just use the greater sign like this. For example, you do echo hello. So it will, if you only do echo hello, it will print out hello in the terminal because the terminal is connected to the standard out. You can redirect that to a file. So when you redirect something, you redirect to a file. In this case, we are redirected to a file. The file name is ASDF. That's a file. So this is equivalent to one greater. In this case, one means the file descriptor one, which is std out, because std in is 0. So those two are actually equivalent. So if you want to append some output, you just use two greater signs. If you want to redirect something from std error, otherwise it will be printed out to the terminal, you just do 2 because that is the file descriptor std error. You can redirect to a file. If you want to redirect from the input, you can use the less than sign. You can have a file, this is a message file, then you redirect the input to the reverse. This is a reverse command. You can do something like that. So we're going to use some of this in the class. And also, a Linux process can also take input from command line arguments, not necessarily just from the std in. It can also take input from command line argument. It can open a file, take input from a file. It can open a socket, take input from a socket. So in this case, we have three commands here, right? So the first one is ls. That's a command. That's also a program. So when you type this in shell, it's actually, the shell is creating a new process using the program ls. And after the white space, what you have that is the command line argument. So when ls, this process runs, it says two command line arguments here. There are two strings. The first string is ls, this string, that's the name of the program. The second string, the -al, that's also a string. That is the first command line argument. So we can say this one is the zeros, this is the first. Then if we do a cat/flag, the command here is cat. It will print out the content of a file, and the file name is just the /flag. you can cat multiple files in together, concatenate them together and output them into the terminal. You can do a cat 1.txt, 2.txt, 3.txt. In this case, we actually have 4 command line arguments, right? 1, 2, 3, 4, and they are all strings. So those 3 are actually also input to the program. Not the content of them, just the string itself is the input to the program. So we also have the pipe operator. So what the pipe operator does is to forward the previous program or process output. So the first program here is echo hello world. The command here is hello. The command line argument is hello world. It will print out hello world to the terminal if we only do this part, right? We print out it to the terminal because we're printed out to the std out, standard out. With this pipe operator, the output will not go to the standard out of the first program. Instead, it will go to the standard in of the second program. In this case, the second program is WC, which is word count. Then we're counting how many characters are there. So then basically by doing this, we are gluing applications together. So in this class, we are going to use those commands. A little bit about environment variable and share variables. Environment variables and share variables are set of dynamic named values, which means there is a key, the name, and also a value. And they are stored in the system, and they are copied to each process when the process is created. So they have this kind of format, the name, which is a key, equal sign. Note that there are no white space. Okay? If there are white space, then the white space become part of the name or part of the value. Okay? Name, equal sign, the value, or other values. You can also have symbols in those values, or sometimes there are multiple values, for example, the pass, right? So the name of those variables are case sensitive. Most values must be separated by the column character, and there's no space around the equal symbol. So environment variables are available system-wide, and as they are inherited by new child processes. Share variables are only applied to current share instance. There are other commands to make them more consistent in different environments. So those are the common environment variables, like user, who is the current user, home, where is the home directory, share, what is the share you're using, pass, the list of directories will be searched when you execute some command. So if we go to our server, we just run any challenge here. We go to terminal. If you print environment variable, use this command, it will print all the environment variables the current share has. You can say, first we have shell. So right now the shell we are running is bash. The current working directory is root. The home directory is CTF because the user is CTF. You can say here, login, your user is CTF. Yeah.
Turn off that light so that it can.
Better? Good. So you can say the user here is CTF, right? There are multiple commands you can use to change the environment variable. We just use print environment variable to print out all, and you can also set environment variables and also export them to different scenarios. So we will talk about them when we use them. Okay. When a new process is loaded into the memory, those command line arguments, those environment variables are also loaded in the memory address space. They are loaded at the very top, a very high memory address, actually higher than the stack you are using, somewhere here. Okay. Those are environment variables, and also you can consider them as local variables of the function calls to your main function. Say developer, you develop a main function. You never call your main function. Say library function will call your main function. And say library functions will load those variables in its own local variables. That's why they are at a very high address on the stack. The executable and linkable file format. So this is a file format we are dealing with throughout the semester. That's why we want to talk about this a little bit. I think we talked about this part a little bit, right? The file name, file extension. Go ahead.
Did you say that the environment variables are higher than the base pointer?
No,
They're in the stack, so they're just.
I'm talking about in a process, they are loaded into the address space, right? You can consider they are loaded by the function that is calling your main function as a local variable. So their address will be very high at the stack. Yeah, because the stack goes down, right? So it has the libc start main function, which calls your main function. Because it calls your main function, it stack variables with higher address of the main function local variables, and also other functions local variables. Yeah. Thanks. So L file is the common file format for executable files, object files on Linux, and they have different extension names, and the extension names do not really matter in Linux systems. There are binary files, kernel files, static libraries, those things. So because they're files, they're just static files on the file system. When you execute a program, those files will be, content of those files will be loaded into the memory, right? So the file has its own file format, and L file is divided into those 4 sections. First one is executable header, program header, sections, section headers. So for example, the executable header at the very beginning, it has some magic numbers telling us this is an L file. And the magic number usually is 7F hex value, then just F. That's it. Okay. The magic number is 16 bytes. Then it specifies what kind of object file type this is. Is this a dynamic library? This is an object file, or this is just an executable? And what kind of a machine architecture this executable is supposed to run? It could be x86, could be 64-bit Intel, it could be ARM, and other information. And there is a tool called the readelf. Use -H, you can read out the headers in a human readable way. For example, if we do this, bin ls, that's the ls command. If we do this, you can find the magic numbers and everything else. So code and data are logically divided into sections, and we already talked about some sections like .txt section for code, .data section for initialized data, .bss for non-initialized data. So for different sections, there are also different permissions. Those sections is writable, readable, executable, those kind of permissions. So you don't need to memorize any of this, right? This is mainly for your reference. Then let's say this is a more concrete example of what kind of sections we have there. So get yourself familiar with those section names. So you say number 16 there, that's .t text. That is where the code is. But other sections may also have code. We have .init number 12. That's initialization code. Usually some C library code. .text is your code. As a developer, your code goes to .text. 17, Philly, that's finish. That's some clean up code by the C library. Also we have elite underscore array, Philly underscore array. Those are arrays for code pointers. And I think after midterm, we are going to do some attack to change those parts. Then we have GOT number 24 GOT. That's the global offset table. Yeah, global offset means those are also functions address in those table. So they are function pointers. So if you can override that, you can also hijack the control flow. 25.data, that's initialized data, .bss, uninitialized data, comments, symbols, those are not that important for security. Let's say what else? PRT, GOT, we will talk about in a minute. And also on number 18, RO data, that's a read-only data section. Because it's read-only, so when that part is loaded into memory, OS will mark that part as read-only. You're not supposed to, no program is supposed to write that part, but only read that part. Right? So we already talked about this. Okay. So there is a feature very important, and as attacker, we are going to use this feature. This is called the lazy binding feature. So imagine you write a program. Your program will use some library functions, right? So when your program is loaded into memory, the loader needs to find out the function address of those library functions, right? So one way to do this is when your program is loaded into memory, we try to resolve or find all the addresses of all the library functions. But the problem is, when you write a program, you're not going to use all of the library functions, right? Then why will our loader waste the time in resolving all those addresses? That's why the mechanism to solve this problem is called lazy binding. So basically, we do not resolve all the library addresses when a program is loaded. We will only resolve those addresses when a library function is called. So when the first time a library function is called, we're going to find out where that library function is in the memory address. Then we put that address in a table. So the second time we call that function, we already know that address because we put it in a table. So we are not going to resolve that twice. And we're not going to resolve other library functions which we never call.
Is this during runtime?
Yes.
Okay.
This is during runtime. So I'm going to show you a demo soon. So to achieve this feature, we use multiple sections. One is called the procedure linkage table, .prt. Another one is the global offset table. So here is this figure explains how it works. Let's say this is .text section. Because it's .text section, this is what the developers coded, right? In the main function, we have a call to puts. Okay. So when you do a printf, sometimes it just becomes puts. Okay. So puts is a C library function. Then this is a C library function. So it is not loaded to the memory when your program is loaded, because this is a shared dynamic library. Other programs may already load this library. So critically, there is only one copy of C library in the memory. We don't have many copies. It's already there. The first time you call this puts function, your program doesn't really know where the function is, doesn't have the address. So this address is not resolved yet. So it actually goes to the PRT table, the PRT section. The PRT section has some code. And this code will first try to dereference a table. And that table is supposed to have the addresses of library functions. If that table doesn't have the address, then it will go to a default stop there, which will resolve that address. Okay. After the address is resolved, it will put that address in this table. So the second time you call that, it will directly go to this address. So we can show a demo of this. Go to our server, then we can go to the, I think I have a source code for that. Lazy, let's go to the 32-bit version. So this is a lazy binding program. If you just run this program, you can see this program is very simple. It makes two function calls to printf. The first function call calls print out first call to printf. The second one print out second call to printf. So this will be the first time in this class we use GDB, I guess. And we're going to use GDB to debug this program. Then you will say, even though we are making function calls to the same program, same function, but the underlying mechanisms are actually different. So what we do is we just GDB this program. We set a breakpoint. We use B to set a breakpoint. We set a breakpoint at the main function. Now we can run this program. R is run. So when we set B, the program is not really running. Now the program is really running. You can say when we set a B there, it has a very short address. That's actually just an offset. That's not a runtime address. But after we run it, you say this address is 4 bytes, right? Because this is a runtime address. So we can do a disassemble. Now you can get a disassemble of this program. This is a main program, main function. You can see in the main function, we don't need to worry about those parts right now. We only worry about two parts. The first one is the first function called to puts. You can see that printf actually becomes puts. Okay. Then there is a second function called to puts. That's it. So we are going to set two breakpoints at those two places. We do a B star, which means this will be our address. We set a first breakpoint there. The second one will be 207. Okay. So now we have two breakpoints. So after you debug, what do? You continue, right? So you use C to continue. Question.
Why are we setting these breakpoints?
I'm going to show you that those two different occasions we are calling that function, we're actually calling into different addresses. Even though that's the same function. If you look at here, that's the same, right? Because we are using the lazy binding mechanism. Yeah. So now we continue. We are at this place, okay? So now if we want to enter that, we just use S, which is a step I, which is step 1 instruction. When we do step in 1 instruction, now you can say we are at this address 6070. Okay, this is our address. If we disassemble here, you can say there are actually 2 instructions. This is a security feature. We will talk about this in the middle of the class. Then there is a jump, right? So if remember this address 6070, if we do this SI again, we're at the 6074. We do SI again. Now we go to some library function, I think, but right now we cannot really disassemble that. There is no symbol there. So, but we can still examine the instructions. We can use the X instruction command to examine the instruction. We can do X / turn I here means I want to disassemble at the current local address, 10 instructions. Current address is basically EIP, right? So when we do this, you can say those are eventually the function we're jumping to 6040. And this is actually the function to resolve the address of puts. So if we do finish, then we can get rid of this, get all of this. Now we're returning for that. So now we are at our second breakpoint, 61 FA. 61 FA, we are here. So we can actually continue. We continue again. Now we are at this place, 6207, okay? Then we're going to step in again, and this time you will say it will be different from last time. Now we step in. At the beginning, we're still at 6070, right? Then we do multiple instructions. You can say this time, we didn't go to that default start function, right? We actually go to the C library function puts directly. Previously, the first call, eventually we went there as well, but before that, we went to the stop. Okay, but now there's no stop. We go to that function directly. This is a C library function, __ GI IO puts. That's a real C library functioning. Yeah, go ahead.
So once the address is like added into the stop, like future calls for the same function gonna like same address for the second one, right?
Yes, exactly. So they will be put in the global offset table. So basically that offset table is full of all kinds of function addresses. And there is an attack we are going to do later is to overwrite that section.
Where is that section?
GOT, global offset table. It has all the C library function addresses.
That's a section in the memory.
Yes, yeah. So section and second, I think we can skip this part because it's not that important to our attack. Manual binary analysis tools. In this class, we're going to use very basic tools, especially in the demos in the class. I'm going to use tools like those command line tools. We just use GDB there. You can use GDB. We're going to use object dump. I already showed you last week. But you can also use other tools in your homework and also in the CTFs. So I recommend you to use Binary Ninja, the cloud version. It's free and it's very easy to use. You don't need to install anything. Just register an account. That's it. You can also use IDA Pro free version, but that one is very advanced. A lot of research we do, we use IDA Pro. But right now, I feel other tools are actually catching up, so you don't have to use that one. Then there's another tool from NSA called Gijwa. So that's an open source tool developed by with Java. So it's a little bit slow compared to the other tools. But Binary Ninja on cloud also not very fast. But they are very powerful tools for you to reverse engineer the programs. So when we do everything in the class, we're going to use obj dump. With obj dump, you see the disassembly of a program. You only see the instructions, and sometimes there are errors. When you use those tools, you can decompile the program into pseudo C code. So it will be easier for you to understand, especially when the program is very big. Then you want to say a pseudo C code. But the pseudo C code may also have errors. That's why you want to compare with the disassembly. So I do have some GDB cheat sheets here for you to use. You don't need to memorize this when you need to. You just I also have several other cheat sheets in my website. You probably already see that. Yeah. Let me see if there's anything I want to mention. Always those two. So in GDB, when you run a program, you just use R. And when you run a program, you want to give command line arguments to the program, you just do something like this. Just R, then command line arguments. But what if the command line arguments you are giving are generated by some scripting language like Python? Then you can use a $parenthesis Python blah blah blah. Okay. If you want to redirect something to that program, you need to use 3 less than signs here. Okay. So those commands we can skip for now. So when you want to run a program in the shell and also use another program's output as a parameter, you do something like this. You type the program name, white space, and the second parameter, you're going to use $sign, parentheses. In that, you will have command. In this case, I will mainly use Python 2. I know many of you are probably using Python 3, but when we are dealing with raw bytes, Python 2 is much more convenient. So in this case, we're just print out the hex value 12, 34, 5 times. So Python 2 is much more convenient. Any questions so far? Good, okay. Then we are moving to our very first attack, buffer overflow. So our very first attack is called stack-based buffer overflow. It's also called the sequential buffer overflow because we are actually sequentially override something by exploiting some vulnerable C library functions. So we will talk about the brief history of buffer overflow, the information a C function need to run different C calling conventions on 32-bit and also 64-bit version. And then we talk about how to overflow local variables. So that is what we're going to talk about today. So next week, we will talk about how to overflow return addresses to execute functions and also execute functions with parameters. Then after that, we will talk about how to overflow return addresses to your own code. We call that share code. And share code will be doing something malicious. So the objectives for this class include understanding how stack works in Linux 32-bit and 64-bit version, and also identify buffer overflow bugs in a program, then exploit those vulnerabilities. Then you take fully control of a computer by exploiting those vulnerabilities. A little bit brief history of this. So this is one of the earliest system and software bugs discovered. People believe it was discovered maybe in the late 70s or early 80s, but was only until 1996, there was a very nice, well-written article called Smash the Stack for Fun and Profit. And this article was published in an underground forum called, or underground magazine called Frank. So this magazine still exists today, and hackers still publish articles on this magazine. So the author who published this used a pseudonym, Alpha1. So that is not really his name, but if you Google, you can find out who he is. So in 1996, that's the first time most people have access to a very well-written tutorial on this topic. Before that, it was like dark magic. But however, this vulnerability has been exploited long before that. One of the most infamous or famous incident was the Morris worm. It happened in 1988. So Robert Morris, so he was a graduate student at Cornell, and now he's a professor in MIT. He works on system, he works on distributed system, and also algorithm design, works on all kinds of things. But before that, he was famous or infamous for this incident. So he wrote this virus or worm, and it took down maybe 50 or 60% of the internet back then. And it was just using a buffer overflow vulnerabilities you are going to learn in this class, meaning what you will learn next week. So even today, this is still a very serious problem. So this is a screenshot I took several years ago from MITRE. This is called the Common Weakness Enumeration, I think, CWE, Common Weakness Enumeration. It lists all kinds of security vulnerabilities, high-level types, okay? Like they can say the very first one is improper restriction of operations within the bounds of a memory buffer. So when you do buffer overrides, buffer overflow, basically you are doing an out-of-bound buffer write, right? You are writing to somewhere you are not supposed to write to. You can also see other vulnerabilities here, like cross-site scripting, that is part of the web security. We do not talk about JavaScript security or web security in this class, because I believe that deserves its own class. You can also say out-of-bound read, user use after free. That is one of the vulnerabilities, especially for heap vulnerabilities. We will talk about this the last two classes of this class. Integer overflow. So many of our out-of-bounds right? So you can see those are still, even now, they are very serious bugs, and they can, if they are exploited, attackers can take full control of the computer. So to understand how it works, we are going to take a several-step approach. First, we understand what kind of information a C or C++ function need to run, right? So to run a function, obviously, you need a code. The function has code, but a function has more than code. It has data, it has parameters, which is also code. It has return values. In C, there is only one return value, right? But actually, you can return multiple values in C. You do not return through that return value, you can return through pointers, right? Then there are global variables, local variables, temp variables. Global variables are not really local to any function. Every function in an address space can say local variable and can say global variables. The local variables are specific to each function and specific to each invocation of those functions. So you have multiple invocations of the same function, they will all have local variables, the same name. But of course, the name only matters at the C code level. When you compare to machine code, they don't have names, right? Then there are return addresses, which is very important. And also, there are two more concepts maybe you are not familiar with. One is called the function frame pointer, or a previous function's frame pointer. We're going to say those later. So variables are declared inside a function or a block are called local variables. So they can only be used by statements inside a function or block of code, right? And local variables are not loaned to functions outside of their own. So did you ever think about how this feature is implemented? Think about this as a feature. This is a language feature. The language provides a feature called local variables. So how compilers and machines can actually implement such a feature? So that is through stack, we're going to say. Then global variables are outside the function. They hold the values throughout the lifetime of the program, so they can be accessed by any program, right? Then there are also parameters. Parameters are basically also local variables. One example, we have a main function. The main function has two local variables. L_i means local initialized variable. It's an integer. Its initialization value is 10. Then there is a L_u, which is uninitialized. So both of them are local variables. Then we have 4 printf functions. After that, we call another function called func. Func takes input 1 integer, p there. Func itself has 2 local variables, and they have the same name as the local variables in the main function. So it doesn't really matter, right? Even if they have the name, they have different scope, so it doesn't really matter. then you print out all the local variables address and also p which is the parameter, yeah, which is also a local variable address. So if we run this program, global local variable, when we run this program, you can see the address of those global and local variables. And you can see those two global variables, they are at the lower half of the memory space, right? The memory space is 32 bits, which is 4 GB. So 8 ASCII letters there, A to F, right? So the global variable GI and GU, they are at somewhere 56, 55, in the lower half of the memory address space. The global ones. Then the local ones, then you can say the main function calls func. The main function, the first local variable is at, so first of all, 4F, which means that's a very high address. Then it is at D6, 8C, right? A pretty high address. Let me finish this one. Yeah. Then you have the next local variable, which has a little bit lower address from 8C to 8 to 88. Okay. Then you go to the func, the another function. The that function's local variable have 5C and 58, even lower address. Okay. The P is a parameter of func, and it has a higher address than the local variables of func, but a lower address than the local variables of main. So the stack actually goes down, right? You call more functions, their local variables were at a lower address.
So how would you say one address is lower or upper?
Just the number is higher. When the number is higher,
But they
Greater?
have letters as well.
what?
What about the letters?
Yeah, those are hex values. Yeah, those are hex values. Any questions? So if you run the 64-bit version of the same program, you will see something similar. It's just the address is much bigger. The address is 64 bits, 8 bytes. So the address are much longer. But you can see the global variables, they're still at the middle. Local variables at a higher address, but not that high. It's not at the very top. It's at a 7F. I think I mentioned in the class last week, the current 64-bit machines, we're not using the full 64-bit address space. We're using like something like 39-bit or 42 bits. That's why here we're saying 7F. Okay. Actually, before that, there should be 2 more zeros. Yeah. Okay, so now we know that those global variables and local variables, where are they stored? And even global variables, there are different types of global variables. We have been talking about this. There are initialized, uninitialized, BSS or data. Then code goes to .text section. Then what is stack? So stack is basically the scratch memory for functions. And this is implemented in different architectures. No matter your phone, your laptop, your smartwatch, their software system all use this stack design. And usually stack starts at a higher memory address and goes down. But most of the current designs is done this way, higher address to lower address. Then functions, they are free to push values onto the stack or store values to the stack. When you store value to the stack, it's called push. When you pop, you are getting some value from the stack. So on x86, we already know that there are multiple instructions to do this. The push and pop, those are the instructions we talked about last week. So push will first decrements the stack pointer, ESP or RB or RSP. So here is a typo, should be RSP, not RBP. Then pop, then it will store the value to that location pointed by the stack pointer. So if you look at the syntax of the push instruction, ESP, RSP is not in the syntax, okay? It's implied there. So when you say push EAX or push RAX, you are pushing the value in the register EAX or RAX onto the stack. Stack is part of the memory. Where do you push to? You push to where ESP or RSP, which are registers, points to in the memory. Okay. When you do a pulp, EAX, then you are pulping whatever ESP points to the register EAX. Yeah.
So because the local variables are at a higher address, does that mean that they're pushed onto the stack before the global variables?
So global variables are not on stack.
Oh, okay.
Global variables are placed there when the program is loaded. So local variables, even for one function, if the function is called multiple times, it will have the same copy of local variable each time it is called. Wow, actually, we will show a demo of that later. So I have a little bit of animation for you to better understand this part. There are 6 instructions we're going to learn in those animations: push, pop, call, return, enter, and leave. Those instructions will change the stack. Enter and leave are not that important. They are just a combination of multiple instructions. The most important is push, pop, call, and return. Let's start with push. So this instruction works on both 32 and the 64-bit. The instruction here is push EAX. Let's say this is what our stack looks like. So value Z is at a higher memory address, X is at a lower memory address. At this point, ESP points to the value X. Okay. Now we execute the instruction push EAX. So what this instruction does is first, it will decrement this register, ESP, by 4 bytes. If it's a 64-bit machine, it will be by 8 bytes. So it will move ESP or RSP down first. Then the value of EAX will go to this memory location. Okay, that's it. Pop is the opposite. We have the same scenario here. ESP, RSP points to the value X. Now the instruction we're executing is pop EAX or pop RAX. So whatever is pointed by ESP or RSP, in this case is X, will go to the register EAX or RAX. And the ESP or RSP will increment 4 bytes or 8 bytes. Okay. So far so good? Okay. The next one is a call instruction. The call instruction does 2 things. We talked about this last week. First, it will push the address of the next instruction to the stack, then move the destination address to EIP, which is a program counter. So this part, we have the stack. And this is a high memory address. This is low memory address. This part, we have the code, okay? Code I'm using, this part is a lower memory. This is a higher memory. So we are about to execute the instruction call EAX. And the stack looks like that. So the call will first push the address of the next instruction to the stack. What is the next instruction? In this case, the next instruction is pop EBX. So we're going to push the address of pop EBX to the stack. So the stack looks like ZYX, the address of pop EBX. Then it will move the destination address to EIP. Destination address is in EAX. The value of that will move to the register EIP, from register to register. Okay. In this case, anyone remember what is this code? What is this code? last week I said there's direct call and what? Indirect call. So in this case, the parameter for this call instruction is a register. Its value is unknown until you execute this instruction, right? So that is called an indirect call. So direct call is the destination is hard coded in this instruction. Okay. If it's hard coded, then you can set that memory region of this code as not writable, then it's protected. No one can overwrite that. But this one, you can somehow manipulate the value of the register.
What is EAP?
EIP is the program counter. Yeah, IP here is instruction pointer. Yeah. Same as program counter. It points to the next instruction to execute. So the opposite operation of call is return. Return is actually very simple. So the return instruction pops the top of the stack to EIP. So the CPU continues execute from there. So it's basically a pop. But your pop instruction, you need to specify which register you pop to. Return, you don't need to do that. It's implied. It is the EIP. Yeah. For example, the code looks like this. There's a pop EBP. Then we're about to execute the instruction return. Okay. The memory, the stack looks like that. ESP points to some value X. So return is basically a pop. We are going to pop whatever ESP points to, which is X, pop that value into the register EIP. Then we are actually executing from X. Okay. Then because it's a pop, ESP will move up, increment 4 bytes. Okay. So that's basically call and return. Make sense? Okay. Let's skip enter and leave for now. We are going to discuss them when we use them. So local variables are scratch memory for functions. So functions, they need to allocate space for those local variables. So to allocate the space, they just change the value of ESP, usually move it down. Then they can allocate that. Then they will use the offset from a lower address to those variables to access those variables. And that lower address is stored in the frame pointer register. In x86, we use the EBP base pointer or RBP 64-bit to store that address. When you see more examples later, it will be more clear. Right now, I know it's quite confusing. So calling conventions decide how parameters are stored on the stack in order to call a function. It decides who stores what information. The callee stores the information or the caller stores the information, who cleans up the stack, those kind of things. We are going to look at the C standard convention first. In this convention, there are multiple functions. One is the function call, other function is called the caller. The function is called callee. So caller will first push arguments onto the stack. Right to left order, okay? The rightmost argument is first pushed onto the stack until the very first argument. Then the caller will execute the call instruction. That's a caller's job. That's a convention. Okay? The callee will first pushes the previous function's frame pointer onto the stack. The previous function's frame pointer is in EBP. So we're going to save EBP onto the stack. Then it will set up its own new frame pointer, basically move ESP to EBP. Then it will create space on stack for its own local variables, just subtract some value from ESP. Then when it returns, it makes sure that the stack is consistent as when it was called. Then it puts its return value in the EAX register. So that's CoreE's job. So we're going to say some examples later. So that's why, because most of the functions, they will follow this kind of calling convention. Compilers will follow this calling convention. That's why the beginning of functions, all functions, and the end of all functions, they look very similar. The beginning of function, we call them the function prologue. Usually they have those three instructions. The first one is push EBP. The second one is move ESP to EBP. The third one is subtract some value from ESP. So EBP, when the first time you enter this function, the EBP stores the frame pointer of the previous function. And you are going to, this function is going to use the register EBP. If you are going to use the register already has some meaningful value. What do? You need to save it somewhere, right? So the way we save it is we just push it to the stack. That's why we have the first instruction, push EBP. Now after that, we set up where is this function's base address, which is, since we already did a push, now ESP points to a new address, and the ESP actually points to the saved EBP there, right? Because we just pushed the EBP. That address will be our new base address. So we move that ESP to the register EBP. So previously the EBP value is overwritten, but doesn't matter because we already stored it onto the stack. After that, we reserve some space by subtracting some bytes from the ESP. So then our local variables will be somewhere higher than where ESP points to. So the function epilogue, we also have usually three instructions. First, we move EBP to ESP. So then we pop EBP, then we return. We will skip this for now because so we can see this example. Let's say that, let me check if I have animations. I don't have animation here. So this is the same global local variable program. Yeah, go ahead.
Does the compiler know how much stack space is going to be required for local variables? Is that
Yes.
Okay.
Yes. So we have the, yeah, go ahead. You have a question? Oh, okay. So we have the main function, right? The main function calls func, and you can say the main function, the func function has one parameter in this case, and that parameter in 32-bit machine needs to be pushed onto the thing. That's why when the main function makes a function call of func, it uses the call func instruction to do that. However, before it does that, it is the main function's job to push the parameter onto the stack. That's why before that you say there is a push A in hex. A in hex is basically 10. Yeah, that's because the main have a func 10 there, if you remember the C code. So that's the quarters part. The CoreE's part, you can say at the very beginning, we have push EBP, move EBP to ESP, subtract something from the ESP. Then at the end, we have that move EBP to ESP, pop EBP, and return. So leave is basically equivalent to those instructions. So in this calling convention, the stack looks like this. Yeah, go ahead.
What is leave equivalent to?
Leave is equivalent to those two instructions.
Mhm.
move EBP to ESP, and pop EBP. So stack basically looks like this. At the top of a stack or stack frame of a particular function, we have its argument. The rightmost arguments are at a higher address. So there will be argument 2, argument 1. If there are more arguments, there will be a higher address. So after that, there is a return address. We have so which instruction put the return address there?
One.
The call instruction put the return address there. Which instruction put the arguments there?
Okay.
The push before the call put the arguments there. Then lower than that, we have the saved EBP. So which instruction put that there?
The move,
Probably.
The push. The push EBP instruction put it there. Then after that, we have the move. The move ESP to EBP, which means EBP will point to the saved EBP. Make sense? Yeah. Then the ESP may be changed. So the base address here is whatever EBP points to. Okay. Then from this figure, you can say the saved EBP is at where EBP points to. The return address is 4 bytes higher than where EBP points to. The arguments are 8 bytes higher, 12 bytes higher, right? We're still talking about 32-bit machine. Then if there is an address which is EBP minus something, if it's EBP plus, let's say, EBP plus 4 is return address, EBP plus 8 is the first argument. Then what is at EBP minus something? That's the local variables. So local variables is at EBP minus something. Yeah. Okay. So the first instruction we have here is EBP minus 8. We are moving from the memory address at EBP minus 8 to register EAX. So guess what is this instruction doing here?
Taking the first.
Variable number 2. Yeah.
Not, it's moving a local variable, but not necessarily number 2, because we don't really know the size of the local variables. Yes, so we are moving some local variable value from memory to the register EAX, the first instruction. The second instruction, EBP minus 24. But the instruction we're using is LAX, load effective address. So we talked about this instruction last week. Anyone remember?
Indulgence.
Get the address. We're actually getting the value of EBP minus 24 to the register EAX. So that is actually an address on the stack, right? The third instruction, EBP plus 8, move that to EAX. What are we doing there?
Taking argument.
Yes, which argument? Yeah, the first argument.
First argument.
Yes. So EBP points to the saved EBP, EBP plus 4, return address, EBP plus 8, the first argument. We're moving the value of first argument to the register EAX. So the next instruction actually is moving the second argument to register EAX. So usually the compilers will generate code for 32-bit machines like this. Another example, we write a simple program to compute the factorial of a particular integer. If you take an algorithm design class, you know you can write a dynamic programming to do this very fast. So here, the approach we are using is recursive calling of the same function. So it will not be a very fast implementation. But this one explain you how function is implemented. So the main function takes 2 arguments. In this case, the first one is an integer, another one is an array of pointers, basically strings. Okay, not only one string, multiple string. So this is actually the command line arguments we talked about earlier. So this program takes 2 command line arguments. If there are no two command arguments, it will just return, okay? So the first command argument is what? Remember? What's the first command argument?
Number,
No,
oh, D.
The name of the.
yeah, the name of the program itself. The second command argument is what you gave there, but what you gave is actually a string, right? So let's say you gave 3 there, that 3 is a letter, it's a ASCII string. That's why we first change that ASCII to an integer, okay? Then we are going to call this factorial function with that number, okay, that's it. So this factorial function will first print out which execution it is. It will print out the parameter's address. There's only one parameter n. Print out the address. Then if n is 1, it will return 1. Otherwise, it recursively call itself, but it calls fac n minus 1 times n. Okay. So let's say if we put fact 3 there, what will happen? We put fact 3 there, fact 3 will call fact 2 will call fact 1. Then fact 1 returns to fact 2, returns fact 1, right? So here we do not really have a local variable, we only have a parameter. And the parameter, you already learned, will also be pushed onto stack. So it's kind of like a local variable. So if we run this program, so one only give one command argument, the name, it print out the error, print out usage. That's why let's do 5. So first, we call the function fact5, print out the address of the parameter, which is at ffffd680. Then fact5 calls fact4, right? So the stack goes down. So the next n has a lower address, d660. Then it calls fact3, which the n has an even lower address, 40, 20, right? So you can see that at a C code level, the parameter has the same name, just n. However, after we compile this, they actually have different addresses. They're different variables. They are local variables or parameters. So another example, we have main function calls a func, and this func takes 5 parameters, A, B, C, D, E. So we just talked about this. Which parameter will be pushed onto the stack first?
The last one.
The last one, right? So E will be pushed on the stack first, then D, then C, then A, then B and A. So if we look at the disassembly of this, 5 parameters. We do not need to run this program. We use obj dump. Intel. We look for the main function because the main function calls func. So this is the main function, and this is a call to func, right? So it's actually hard coded in this case. The main function calls func 1, 2, 3, 4, 5. So the main function will push 5 first, then 4, 3, 2, 1. Then make the function call to func. The func will actually use those addresses to the function func. Where are the parameters? They are at a location higher than where EBP points to, right? So it is actually EBP plus 8 plus say 10, 14, 18 in hex. They're actually retrieving values from the stack, retrieving those parameters. So you probably already sensed that there are many different ways to implement this. So the say declare the say standard convention is just one way to implement this. The disadvantage of that is every parameter goes to stack, which means every parameter goes to the memory, and which can be a little bit slow, right? So that's why 32-bit version, they actually have a fast convention. If you develop a say function, you want it to be a little bit faster, you can use the attribute fast call. Then it will not use the standard convention we just saw. In this convention, we are going to pass the first argument in the register ECX and the second argument in the register EDX instead of pushing them onto the stack. However, for 32-bit machines, we do not have so many general registers. That's why we do not really use this very often. However, on a 64-bit machine, there are so many general registers. So we do not need to push things onto the stack anymore. Okay, we do not need to put everything onto the stack. So the standard calling convention for 64-bit machine, the first 6 parameters do not go to the stack. They go to those registers, RDI, RSI, RDX, RCX, R8, R9. Those registers were not available on the 32-bit machine. Well, RDI and RSI actually were available. Those two also available, the 32-bit version, but there are not enough registers to do this. Yeah.
So what if there's a recursive call
Yes.
that's being made? Let's consider the factorial program.
Yes.
So, okay, the first, let's say we are passing 5 to 6 arguments.
Yes.
So the first caller function would use all the registers that are available for the arguments, right?
You're talking about the 64-bit?
Yeah.
Okay.
And what happens when the second function is making a recursive call again?
So when you run out of registers, what do? You still have to use memory. Yeah. So the compiler will notice that, then probably will just choose memory to do those things.
But the first caller function, the
So
values.
actually, in this calling convention, the compiler will still use registers to pass parameters. But after passing the parameter, when you enter that function, it realizes I do not have enough registers. I still need to push them onto the memory, the stack. Then next time it call the function again, it will use register again. But when you go there, you realize, oh, I don't have enough memory and enough registers. I'm going to use stack.
Okay.
Yeah, so it may not make it much faster in that case. Yeah. So this is a 64-bit version of the same program, exactly the same program. Remember the previous one, we saw the pushes, right? Push 5, 4, 3, 2, 1. Now let's look at, and also we can look at how big this program is. This is a func program, 32-bit. It's like maybe 15 instructions there, right? A lot of push, a lot of and here is not really push. There is just a lot of move, reading from the stack. If we look at the 64-bit version of the same code, the same C code, the same code, we go to the main function. Yeah. Where? Yeah, that's right. So this is the main function of the 64-bit. You can say we're not pushing those parameters onto the stack. Instead, we're moving 5 to R8D, 4 to ECX, because the higher 32-bit are already 0, but we're actually moving to RCX. Then also other values, can say. Yeah. Then, but you can see the compiler here is doing something actually stupid. It's not directly, we're trying to add them together, right? So the smarter way to implement this is you just add them together. But in this implementation, the compiler is moving those values to the memory again, then add them together. That's because of the optimization levels. We use a higher optimization level, the compiler will be smarter and fewer instructions. Okay, finally, let's take a 5 minute break. Then when we come back, we are going to do our very first attack. We come back at 7:20. So what? When we put in form, right? So the push happens at the lowest area. So push, we're decrement the ESP and add value there. Right. So the stack actually goes down. Okay. Yeah. But we did not show it in diagram or anything. The push happens at the bottom. What do you mean by push happens on the bottom? Like when we push ESP, when we ESP was going down. Yes. Like ESP was going down, but when you consider stack, it's like first and last step. Yeah, that's actually, the bottom is actually called the top of the stack. Yes, a little bit confusing. Okay. So think this way. Let's say you are stacking plates, right? You are putting plates on top of each other, you are stacking them. So what you say is the top of the stack. But in memory, we just flip it. Okay. Yes, so the top of stack is at the bottom. Okay. Yeah, adding things there. Okay, so the top. Yeah, that's why I try not to use those words like top of stack, these words, because you were being very confused.
Sure, there's gonna be no water bill. Honestly, I shouldn't have doubted it, right? I'm not curious.
I'm just asking, I did not see the screen charts, but I did this.
I wanna say screenshot in the future.
Okay, yeah.
Because I wanna see you actually did this. I feel like I should have talked about this. Okay, so now you have a pretty good understanding of how function frame works. So it's time to look at our very first buffer overflow example. So in this example, we're going to do a data only attack. We're not going to overflow addresses, code pointers, those kind of things. We're going to overflow some data, that's it. And in this example, we're going to do a sequential overflow. So not all stack overflow will be sequential. Sometimes it could be other pointers to enable you to do something more malicious, but we are going to start with something sequential. The program we are going to use is this overflow local one. It's a very simple program. We have a main function. The main function first check if there are two arguments. If there are, it will call the lawful vulnerable function. Lawful takes two arguments. So you can say the first one is an integer. The second one is a pointer. So on a 32-bit machine, what's the size of those types? Integer is 4 bytes, 32-bit. How about pointer? The same, right? So that. Does it matter what kind of type of pointer it is? It's an integer pointer, float pointer, doesn't matter, right? Pointer is 4 bytes. Right. Then we have a local variable, j. The first thing we do in lawful is we assign the value of I to j. Now after that, we have a local buffer. We call it buff. It has 6 bytes. At a C code level, it has 6 bytes. There is no guarantee the compiler will only generate 6 bytes. The compiler guarantees that it is at least 6 bytes. So the compiler, for alignment reasons, sometimes make it a little bit larger. But here, SQL level 6 bytes. Then we have a function called string copy. Okay, copy from a destination address to a source address to a destination address. The source address in this case is P, which was specified in the parameter. And P actually points to what? argv1. What is argv1? User input from where? Command line. That's a command line argument. So the very first command line argument, the name of the program is argv0. The second one, the prompt is argv1. So the tricky thing here is you don't know how long this user input is, right? So user input could be super long. It could be 6 bytes, it could be smaller than 6 bytes, it could be super long. But the buffer we have there actually only guaranteed for 6 bytes, maybe a little bit bigger, but only guaranteed for 6 bytes. Then we're going to copy whatever you input to that local buffer. But that buffer may not be big enough to hold your input. That's why we have our first buffer overflow there. Then the value was initialized to 0 here. All right, that's why j also will be initialized to 0. So after that, we will check the value of j. If j's value is 0, we will print out, the program will print out IPT the full. If the j's value is not 0, it will call the function print flat. Okay. So because this is a set UID program, print flag will actually read the flag file and print out the value for you. So that's the C code. So then we are going to look at the binary code line by line to understand how this program works. Before that, let's look at what the string copy function does. So this is a function you should not use anymore. It's still part of the C library, but it's a dangerous function that you should not use anymore because it will trigger those kind of overflow. This function takes two parameters, the destination and the source. Then it will copy every byte at the source address to the destination as long as that byte is not zero. That's it. As long as it's not zero, it will copy. Okay, it will keep copying. So this is a implementation of that. Of course, there is a shorter implementation, something like this, but semantically they are equivalent. Okay, just the copy from source to destination. It doesn't matter how long the source is. Okay, what only matters is it will end copying when it's say a zero. That's it. Then let's look at the instructions of this function one by one. So the Overflow was called by the main function, right? So before the main function calls Overflow, the specific call function, what does it do? What did it do?
Which is, yeah,
Push two arguments, right? The first argument is the address is P, okay? The second argument is I. Actually, the first argument is I, the second is P. So we push P first, we'll push I next. So P's value, we don't really know. I's value, we already know is zero, right? So as stack right now looks like this. P, zero. Then after that, we have the call instruction. The call instruction will put the instruction after the call instructions address onto the stack, right? Then give the control to the function Overflow. Because before we execute Overflow, before we execute the very instruction push EBX, the stack looks like this. P, I, and the return address, right? The actual value of the return address right now doesn't matter, but we know here we have the return value, okay? And the ESP points to this. Then we execute Overflow. The very first instruction of Overflow is push EBP, right? So the EBP's value will go to this place. We call that the old EBP or saved EBP. And because this is a push, ESP will move down. So ESP points to this saved EBP. Then the next instruction is move ESP to EBP. So ESP was here. We're moving it or copying its value to EBP. So EBP now also points to here. Previously, EBP points to somewhere higher, okay, which we're not showing in this figure. Now, after this instruction, both ESP and EBP point to the same address, which is a saved EBP. The next one, we subtract some value, constant value, hard-coded value from ESP, which in this case is 18 bytes. 18 bytes, no, 18 in hex, which is what's that? 24 bytes, yeah, 24 bytes. Now we move EBP plus 8 to EAX. What is EBP plus 8?
The first argument.
Yes, EBP plus 8 is the first argument. We move that value, which is 0, to the register EAX. So now register EAX has a value 0. Then we move EAX to EBP minus C. Why we're doing that?
if we are assigning J,
Exactly. The EBP minus C is our local variable J. And we're assigning I's value to J. Okay? So by looking by looking at this instruction, you figure out, oh, J is at this address, EBP minus C, okay? So we already say that ESP is basically EBP minus 18 in hex. Then EBP minus C is at a somewhere higher than where ESP points to, okay? So now we know that local variable J is at EBP minus C, and now it has a value 0. Then what is the distance between, how big is this local variable? 4 bytes, right? Then what is the distance between this local variable to the saved EBP?
40.
No, this is C, right?
Well,
C is 12. Then it used 4 bytes. No, so it should be 8, right? So this part will be 8 bytes actually, yeah. Then we have another subtract, 8 bytes from ESP, so ESP moves down. So actually ESP right now is at EBP minus 20. Then we push EBP plus C to this address. Then EBP plus C is the second parameter, which is P. We push P to this address again. Why are we pushing it? Go back to the function, C code. This is P. So here, did we use P? We use P here, and P is a parameter, the second parameter. So we need to push this parameter, right? We need to push P. We also need to push buffer's address. So we're going to say 2 pushes there, right? So the first one is push EBP plus C. Then we get the EBP minus 12 to EAX, okay? Then we push EAX. Why we're pushing EAX? EAX is a buffer. We're pushing a buffer, which means EBP minus 12 is where the buffer is, right? So EBP minus 12 in hex, that's where the buffer is. Then the local variable J is at EBP minus C, okay? Then what's the distance between them? 12 is basically, 12 in hex is 18 in decimal, C is 12. So
6 bytes.
there are 6 bytes. So in this case, compiler gave us exactly 6 bytes. That's what we asked for in the C code. So the buffer size is 6 bytes, right? Now after that, after those 2 pushes, we make the function call to the vulnerable function string copy, okay? What will string copy do? It will copy from the source to the destination. And the source is at, the string copy, of course, its own function. That's why its stack will be somewhere down there, right? But it's going to copy from the source to the destination. And the destination is a local variable in Overflow, which is at EBP minus 12 in hex. The source is somewhere very high, higher on stack. We only know its address. We do not say how big it is, right? So the string copy may do something dangerous. It may copy more than 6 bytes, right? If it copies 6 bytes, what will happen? It will just overwrite buff, right? Actually, it can only overwrite 5 bytes because string copy will append a 0 at the end, right? So then if we input more than 6 bytes, what will happen?
It's gonna overwrite whatever's under it.
Yes, we will overwrite. First, we'll override the local variable J. Make sense? If we keep doing that, we actually can override the saved EBP. We can override the return address. We can override other things. And go up, there are more functions, return address, everything we can also override, right? But we're not talking about that today. We will talk about it later, but mainly talk about overriding the local variable J here, okay? So then when this function comes back, when this string copy comes back, we will first add ESP10. So ESP goes up to here. So try to balance the stack. Then we compare 0 with EBP minus C. That is, what is EBP minus C again? J, right? So we're comparing if J has a value of 0. If J has a value of 0, we will print out IPT the full. If J doesn't have the value of 0, we print out the flag, basically, right? So then let's run this program. Overflow. Overflow local 1. When we run this program, we do not give any command line input. It will not do anything. If we do 1, 2, 3, 4, 5, what I give is not really a number 1, 2, 3, 4, 5. What I give is a string. That string is 5 bytes, right? So when I do that, it will not trigger any buffer overflow. So it will be IPT the full. When I do 6, what will happen?
It'll overflow.
It'll print the flag.
IPT the full still.
Yes, both of you are right. We do overflow, but the value will overflow will still be 0.
Zero because it's
Yes.
final. Yeah.
So we do not really, so it will still be IPT the full. However, if we do a 7 there, we will get a flag, right? So what if we do more than that? What will happen?
Segmentation fault at one point.
Yeah, why do we get a segmentation fault here?
The
Go ahead.
stack will be written, the return pointer will be written over.
Yes, so when we do something like this, actually before that, we overwrite the saved EBP, and that may already trigger the segmentation fault. Because saved EBP is also a pointer, is a data pointer, right? It's pointed to a data structure technically, it pointed to the previous function's stack frame. But in that data structure, there is a return address, there is a code address, right? So also here we have also another return address. So we have put garbage value here. Then when those pointers are dereferenced, those address may not exist. There is no physical memory backing up that address. That's one reason to trigger the segmentation fault. Even if those addresses are backed with some real data, you may treat that whatever there as a code, but they not be valid code. Those code may trigger segmentation fault, right? That's why we get segmentation fault. So here it doesn't really matter what, but before that we already get the flag anyway. So it doesn't really matter what value we put here, right? As long as it's longer than 6 or 7 bytes, we get the flag. That's really what value is. Yep.
At the very start of the function, I think the third line, we made like the function made for 24 bytes, right? In the stack.
12 bytes,
24.
24 bytes, yeah.
So stack pointer minus hex 18.
Mm-hmm.
And we only have 2 local variables. With like 1 integer and one buffer of 6 bytes.
Mhm.
Why 24 bytes?
So the compiler has many reasons to do that. For example, for alignment reasons, to different architectures, they may run faster when you align them at different locations. For example, they may run faster when you align the 16 or 32 bytes, because at a circuit level, it's designed that way. So then the compiler has those kind of information. That's why the compiler will utilize that to generate faster code. Even though in this case, the code, the runtime memory consumption will be a little bit larger, but it may be faster. Yeah. Okay, so then let's look at the 64-bit version of the same program. It's actually very similar. Let's see. This is Overflow. The very first instruction is push RBP, then move RSP to RBP. That's the same thing. Then we subtract 32 bytes in decimal to RSP. Then we move RDI to a local variable, RSI to local variable. Those are the two parameters. They are in RSI and RDI. Then we move the value. This one should be. Which one is which? Say. The RBP minus 14 is I. RBP minus 20 is the buffer in this case. Move I to EAX. So then move EAX to RBP minus 4. So in this case, actually J is at RBP minus 4. Okay. Then move RBP minus 32 to RDX. Load effective address RBP minus A to RAX. So actually, the buffer is at RBP minus A. Okay. RBP A is what? A is 10, right? So from buffer, the beginning of buffer to saved RBP is 10 bytes. And in that 10 bytes, we have 4 bytes for J, which is RBP minus 4, right? So actually, in this case, even 64-bit version, the buffer is still 6 bytes. Okay? The compiler is generating 6 bytes of buffer in both cases. Then we do the string copy. So that's why the exploit will be the same for both programs. Overflow 164. Six is fine. 7, we get the flag. Okay. Okay, next example. The only change here is the value J, we do not check if it's 0. Okay. We check if it is a very specific value. 1, 2, 3, 4, 5, 6, 7, 8 in hex. Only if J is that value, we're going to print the flag for you. Okay. So I will give you 10 minutes to work on this. Yeah. So what is the idea here?
You get it to, you put in the amount of characters for the buffer.
Yeah.
And then exactly those digits in hex.
Yes, exactly. So that's the idea. But what do you need to pay attention to here? Order. Yeah, the order. The little endian, big endian, you need to pay attention to that. Yeah. So you can use Python 2 to do this. You want to convert it to decimal? Yeah. You don't have to. You don't have to. Yeah. So say, yeah, you are inputting a string, right? It's not. You are not really inputting the value. How do you input the value there? Yeah. How do we do that? You are also inputting a string. Yeah, 1, 2, 3, 4 is a string. So other input value. When you times 5, that's not the value you want.
This is game character.
And that's a hex value, that's a hex value.
So it's 1, 2, 3, 4.
Yeah, that's the hex value. Yeah, but you're times 5 means you're doing that 5 times.
Oh, okay.
Yes, that's the syntax of Python. Yeah. Just try to give it some input. First to say if you can crash the program. Yes, that's ASCII. So, looks like the first challenge everyone has is you are inputting the ASCII value 1, 2, 3, 4, 5. You are inputting a string. So how do you input the number? Okay. So what you do is you can use this syntax. You use Python or any other script language you are familiar with to print out a value. I'm not giving you directly the export here, but should be the syntax is similar. Use a dollar parentheses Python 2, then -c basically means this is a script mode or whatever. Yeah. Then print, then /x12 means you are printing 1 byte, and that byte has a hex value of 12. That's it. Then /x34, you're printing out 1 byte, which has a value, hex value of 34. Times 5 means I'm going to print out 10 bytes. You will have the 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That's obviously not what you want in this case, right? But that's the syntax. That's on the next page of the slide. Got it?
Now I'm just trying to understand this.
Okay.
Sorry, Professor.
Cool. First flood of the semester. Yeah. Okay, say, and what you have? Show me that. Oh. It's because it's one. So you can do byte by byte, to make sense easier. Yeah. Because you're doing a huge number. Yeah. Don't forget about filling the buffer first. Yeah. Okay. So first you need to fill the buffer, right? How do you fill the buffer? And does it really matter what you use to fill the buffer? No, the syntax is not correct, first of all. Oh, you're trying to do this, okay. It's easier to just write something here instead. Yeah. Yeah. Correct. So it says legal onion. First of all, why do you swap 7-8 to 8-7? That's in one byte. You don't need to swap things. Right? Yeah. Yeah, that's in one byte. You don't need to swap things.
Then I can move about things right.
It's not good getting there.
Oh, yeah.
Yeah. Yes. Got it. So you guys. Segmentation. Oh, yeah, so because you are feeding 1, 2, 3, 4 times 5, you're not feeding. You know, you say 1, 2, 3, 4, 5, 6, 7, 8. That's what the program is asking for. Yeah.
The reverse order of bytes.
Let's go. As long as you get flag, doesn't really matter. You get a segmentation, but why do you get a segmentation? What big difference to go? When you guys get a flag, do you also get a segmentation for it? No? Oh, yeah, yeah. Oh, this is 64. Oh, I see. Yes. Maybe it'll be
The other one needed 6, so I just put 6.
You got it?
The previous examples, they have the buffer size of 6. So it's-
Yeah, one behind. Show me where you have. Because you're getting a string there. It's not there. This is the ASCII string. So let's for the one. What is one? One is basically 61 in hex.
Oh, yeah.
We're looking for 12 in hex, not 61 in hex. So here, 1, 2, there are 2 bytes. There, 1, 2 is 1 byte.
Oh.
Yeah. Okay.
Got it.
What? Right. You forget about the buffer. Yeah. First is the buffer. Okay, try this again. Okay, why it's not working? Endianness. This is a little endian machine. So the higher byte should go where?
I see, so they should be swapped.
Yes, so the higher byte is 1, 2, 12, right? They should be swapped. No, not swap like this. You are swapping. So 1, 2. So no, can draw here.
Yeah. Oh, sorry, you're.
Okay. So this is 1 byte, right? This is another byte. It's not going to stay here. This is another byte. So this is a lower byte. This is the most significant byte, right? So most significant guide should go to where? Higher memory address, right? So it should be this.
Oh, okay.
right?
I always get confused about what
Yeah,
gets inner.
exactly, yeah, not swap. Okay, do that. So,
What does it-
so here, this program, so you're trying to type into the program, you say? Is this program taking input from STD? No, right? So, go to the slides, that's why I have one. Now,
But the unit gonna be different.
so this program is not taking input from STD, so you don't type into that. This program takes input from the command line argument, and this is the same thing. Command line argument. So what is slash x 66 8? What is that?
Keyword, yeah.
Okay, so what is slash x? So slash x is going to give you the hex value, right?
Okay.
So in this case, slash x 66, you are going to get 1 byte. The hex value will be 67, okay?
Oh,
Then what is 8? Then 8 slash x will only followed by 2 digits. 8 will not be part of that anymore.
oh,
8 will be another ASCII character, which will be 88 or whatever. Yeah.
So you.
You got it? No. Where are you?
Very silent, yeah.
Which means flag is getting one. But then
So first of all, you forgot to fill the buffer. Remember, there's a buffer, 6 bytes, right? You need to fill the buffer. Then the emptiness. So the higher, the most significant byte will go to a higher address. Yeah. Think about that.
TDI is the second one.
Keep trying.
See, yes, I.
Mhm. Okay. So first you want to fill the buffer, right? What is the buffer? 6 bytes, 6 bytes. Then you want to 6 bytes of garbage, whatever it is, okay? So right now, so this, is this 6 bytes?
Yeah.
We do this, is this 6 bytes? Can't write here?
Sure, yeah.
You did is slash. It is slash x
Yeah.
99999, right? Yeah. This is 6. But how do we interpret this? This part is actually 1 byte. Right? This byte will be 99 in hex.
Yes, there's a bit, I know.
This one is what? It's ASCII. Then this one is ASCII. This one is another ASCII. So ASCII is 2 digits, right? 1 byte. So the whole thing is actually 5 bytes. Right? This whole thing is 5 bytes, not really 6 bytes. Then for the other values, it's better you do, now you just separate things really easy. Instead of writing 1 become. Yeah, I read 1 number should work, but 2. You got it.
I bet you need one on the outside of the good stuff. Cause that's. Two things. What? There in the space you have. No.
Right now, putting in 6 bytes
Mhm.
to fill the buffer and then whatever.
Yeah.
There's
It
a
is
space here.
giving you the flag version first.
Yes.
So the-
Yes, I think the reason is because at the end, there will be a new line or 0 when you print out that.
Oh,
Okay.
byte from print.
But the 64-bit version, the buffer is exactly, remember when we did it's exactly 6 bytes of buffer, 4 bytes of data, then you will be saved RBP. So you are actually overwriting 1 byte of saved RBP. Yeah, and that 1 byte is causing the segmentation fault. Yeah. You got it, right?
Yeah, 32.
Okay.
The.
Show me the one you have.
So what's the beginning of it?
Doesn't matter. I'm just showing some examples. Yeah.
The extra.
Yes.
That means you are trying to output that hex value. It may have an ASCII character responding to that, but not necessarily. I was not trying to mean anything. Yeah, I just showing examples.
Okay, sure.
Show me your export, what you have.
You go to the six, right?
Okay. You forget about the buffer. You need to fill the buffer first. Okay. You get?
Yeah, I got the 32 on 64 now.
Okay, it's the same.
Yeah, I want to interpretation.
This is not what you give to the 32-bit.
Oh, no, I actually forgot.
Yeah,
Now
it's
I-
exactly the same. You remember, first to have the buffer, 6 bytes of buffer. Yeah, not that at the end, that is the beginning. Yeah.
That means like when you press enter, it thinks it's part of the command. So it's-
We have this.
Yeah, we're good.
Seven times.
Okay, so most of you got this, so let's let's say the 32-bit and the 64-bit. So I say, you make all kinds of mistakes. So first of all, this program takes input from where? Command line argument, right?
Yes.
It's not taking input from the STD in, standard in. So you do not pipe into the program. Right? If you pipe into the program, the share actually will, say there is an error. So this is true. Over. Oh, no. So this program, you actually take input from the command line argument, not the standard input. So if when you do this, you try to pipe into that, you're trying to give it a standard input, it will actually get some. Is this one? This one, right? Overflow local 2. Yeah, this is a program. So it will not work, right? Because the input should be from the command line argument. So if you have a command 1, 2, 3, 4, 5, 6, 7, it will say IPD the full. And what you need is to input those bytes here. So after print, you can input whatever you want. So the first is you need 6 bytes of garbage, right? But that garbage cannot be 0. Anything else is fine. So I'm just put A there, then times 6. Okay. So if I do this, is a what's the syntax error?
No, but that's what it's saying there.
Two.
Yeah, Python 2.
What? Oh, Python 2, sorry, yeah. If I do Python, it will be Python 3. So Python 3 is totally different syntax, yeah, okay. So if I do 7, it will be the same. So 6 bytes of that. Now after that, we will have 4 bytes. So the most significant byte here is 12, which means it goes to a higher address, which means you should input that last because it's going to a memory copy. The first input will be first copied, it will be at a lower address. So you will do 1, 2, 3, 4, 5, 6, 7, 8, right? So when you do this, you get the flag for the 32-bit version. And if you look at we have the code for the 32-bit version. Oh, we don't have this code for that. The 32-bit version, it will not give you a segmentation for it, but 64-bit version will actually give a segmentation for it after print out the fact. So your goal here is to get the fact. So it doesn't really matter what buffer you use. You can use A, you can use C, you can use whatever you want. You can use another hex value. 23, right? It works. Let's say if you can print out one, oops. 3, 4, 5, 6, 7, 8. Why this one is not working?
You don't need to character after X.
Yeah, you want to?
Yeah, that was the,
Yes, so basically in this syntax, you can only input one hex byte. So when you do this, you are not inputting the whole thing as hex value. You are inputting this part as 1 byte, which is 12 in hex. Then you are inputting a ASCII letter, ASCII character 3. What is ASCII character 3? That's 33 or something, right? ASCII table. Let's say three will be where 3? 3 here. 3 would be 33. Okay. So how do we prove that? We can actually prove that. So let's say we don't do this. We get the value. So this will print out the value to the terminal. See? 3 is a ASCII value. Okay. But it's 1, 2. So this one we're showing 6. This pound here. But that 1, 2 is not printable. If we go to the ASCII table 12, you can say 12 is actually form feed. So it's not printable. That's why you do not say anything here. Okay. But you can actually verify that with other tools like XXD. If you use XXD, you can say 23, 23, 23, 6, 23, then 1, 2. Okay, but 1, 2 is not printable. That's why here it will show a dot for everything. But here it doesn't show anything. Okay, makes sense? Yeah. Yeah, so that is for buffer overflow local.
Why do we need to overflow the buffer for this one?
Why do we need to overflow buffer?
Yeah.
Because your goal is to overflow the local where is that? Your goal is to overflow the local variable J, right? But the string copy do not directly write to the local variable J. The string copy writes to the local variable buffer. That's why you need to fill this, right? Yes, that's why.
so I get that it's a little endian, but I don't understand how Python is translating, how like what's coming out of Python is translating into something that it understands is a memory address that it needs to like flip around, or is like the way that it's inputting from
Okay.
Python.
So it's not really about memory address in this case,
Okay.
right? So
Or I guess how does it know that it's hex and then it needs the way that it's inputting these is
Okay.
gonna be in that order, because it doesn't do that for the buffer for the like random characters. It's not doing that. So how does it recognize that this is a hex number?
for buffer, that's an array of characters, an array of ASCII.
Yeah.
There is no such concept of endianness.
Right, and
It's
so
just
how
one
does,
by one.
so why is
Yeah,
this?
But
Where-
why this
yeah.
one has?
Yeah.
Because here we have a value, the value has 4 bytes. Then the most, in little endian, the most significant byte goes to a higher address. Okay, the least significant byte goes to lower address. Okay, then the value we are trying to input is this 1, 2, 3, 4, 5, 6, 7. 8. What is the most significant byte here?
1, 2.
1, 2 is the most significant byte. So it should go to a higher address, right? Okay. So now when we input this way, which is the correct way, the first byte will go to a lower address.
And it knows to do that because of the escape character. The /x.
Actually, no. So even if we know the escape character, the 7, 8, the 7 basically is 1 byte, right? So in this case, with the escape 7, 8, this is 1 byte, right? You get that? This is 1 byte.
So I see why it's 1 byte, but I don't understand, like, you're saying without the escape character. How
Without
does it
this-
know that it's not just more random characters, like it's not just C times 6
So
again?
let's say without those characters, then we have, let's say, what, 5, 6?
That looks like a random array of characters to me.
This is that's correct. This is a random array. This is an array character.
Yeah.
So 7 is at a lower byte.
Mhm.
Then 8, then 5, then 6.
Mhm.
Each of them is 1 byte. Yeah.
So how does it know that it? I'm not following what is coming out of Python and what's going into the thing such that it's not a random array of characters and it is something that is ordered into bytes.
So you can consider all of this as an array of bytes. Do not
Okay.
consider this as a number. This is an array of 4 bytes.
Okay.
Okay. So this is the
And
first
is
one.
the C times 6 also an array of bytes that the exact same thing is happening to?
Yes.
And so why isn't the C times 6, like the first C is the,
Because the value doesn't matter. The C value doesn't matter, right? That's to fit in the buffer. So whatever you give there will be fine. There-
okay, I think I got it.
Okay. Any other questions? So it can be C, it can be whatever, right? We only need 6 bytes. That's it. Yeah, whatever, 6 bytes.
And when it does this, those 6 bytes are gonna be basically ordered such
Yes.
that it's gonna go from,
The first shows up will be at a lower address.
right, so it's gonna be 6 at the lowest, then 6 again at the next lowest, and 6 again at the next lowest for 6 bytes until it gets to the 7, 8, and that's gonna be the next lowest, and then 5, 6, and then 3, 4, and then 1, 2 is gonna be the highest.
Yeah, something like that.
Okay.
Yeah. So
Okay.
here actually I should not times 6 because we only need 6 bytes. So yeah, this will be low, 1 byte higher, 1 byte higher.
Okay,
Okay. Now we can move on. Okay, let's see. So I want to show this figure again. I showed this last week, right? So I said that what we're doing this semester is actually captured in this figure. So what we did was basically, we first get a pointer go out of bound, right? Where is that pointer go out of bound?
after the buffer.
Okay, at the cycle level, where is that pointer go out of bound? What are the pointer is that?
Override?
Yes, the pointer is actually in that string copy function, right? Because the string copy function is writing to somewhere and it has a pointer. And we get that pointer out of bound. It's supposed to only write in the buffer, but now it goes beyond the buffer, right? Then we use that pointer to write something. And what we're writing is only data in this case. We're not writing code, right? Then we are writing some data we specified. Okay, attacker offered specified data there. Then we use that to corrupt some local variable in this case. So this is called a data only attack. That's what we did just now. Okay. So in the homework this week, there are multiple challenges like this. There's no source code for you. You need to disassemble that. Yeah. So start early. So the next hour, we are going to move to return address. Okay, so the next attack we are going to learn is to override the return address. We do not only override the local variables. We are going to override the return address. And now we are not overriding data. We are overriding some special control flow sensitive data. So this is called the control flow attack. We already know what is a saved EBP or saved RBP. Then we also know the return address. The return address is basically the saved EIP, right? We just call it with many different names. So there is nothing right now to prevent the attacker from overriding those values. Actually, we already overrode those values and we get a segmentation fault. Our goal is not to get a segmentation fault. Instead, we are going to override to some places that we can do something malicious and we do not get a segmentation fault. The goal is to override the saved first. We will go override the saved return address, save the EIP. Next week, we will learn we do not have the ability to override the saved EIP or return address, but we have the ability to override the saved EBP. How do we attack this? So the program is called Overflow Return One. Similar program, I'm just using different vulnerable functions. In this case, I'm not using string copy, I'm using gets. So gets take input from std in. It doesn't take input from other places, but it's the same, okay? It stops copying until it reaches the end of the line, which is a 0, okay? So in this case, the main function first print out the address of print flag is at some location. So in this address space, there is already the function print flag, okay, somewhere there. Then it calls Overflow. Overflow has a buffer, maybe 6 bytes, maybe more. Then it has gets to buffer. So we know that it's a buffer overflow. There is no local variable, other local variable for us to override. So after overriding buffer, we're going to override the saved EBP and the return address. And that's our goal. If you do not get a flag, you do not trigger segmentation fault, it print out IPT the full. That's it. Okay. So gets will read a line from std into the buffer until either a terminating new line or end of file is reached. Then it will replace with 0. I think it will make sometimes it will override. It will print 2 letters there. I think. Okay. So let's look at the stack. Before we call Overflow, the stack looks like this, right? The main function calls Overflow. Overflow has no parameter, so the main function didn't push any parameter. So ESP points to the return address. Okay. Then the first instruction, let's skip that. The end BR32, that's a security feature. But it's not really effective at this moment. And we will talk about it later. So the real first instruction is push EBP. So we have the saved EBP, which is the main function's EBP. Then we move ESP to EBP. Both of them point to that. Then in this case, we save 24 bytes. We subtract again. I don't know why the compiler is doing this, but this is what we are saying. Okay, it's not smart. You can say the compiler is not doing smart things. It can easily combine this, but it didn't. Anyway, so that will be another 12 bytes. Now we have 36 bytes. Okay. Then we load the effective address of EBP minus E to EAX. Then we push that EAX. And we know that EAX is the address of buffer because the next function call is gets. So we know buffer is at EBP minus E, okay, which is EBP minus 14. Okay. So which means the buffer is actually 14 bytes in this case. In the source code, we asked for 6 bytes, right? But actually, the compiler gave us 14 bytes from the beginning of the buffer to the beginning of the saved EBP. That's 14 bytes, which means we want to overwrite the saved EBP, we need more than 14 bytes. But our goal is not to overwrite the saved EBP. Our goal is to overwrite the return address, right? So let's say after we make that get call, we write something to this place. Eventually what happens, when that get returns, it will balance the stack, move the return address, not return address, return value, which is 0 to EAX. That's setting the return value. Then only 2 more instructions. The first one is leave. Leave is equivalent to in 2 instructions. One is move EBP to ESP, another one is pop EBP. Okay, so let's say right now, after move EBP to ESP, both EBP and ESP points to the saved EBP again, right? After that, we pop EBP. What is pop EBP? Whatever ESP points to will go back to the register EBP. So pop EBP, this instruction is actually restoring the previous function's frame pointer. So what is saved on stack? The saved EBP goes back to the register EBP, and the ESP moves up 4 bytes. So ESP now points to the return address. The next instruction we're going to execute is return. Okay, so return will pop whatever ESP points to EIP. So we will start executing from there. So this is what our exploit look like. Our exploit will first have 14 bytes to fill the buffer, right? After that 14 bytes, we have 4 bytes of saved EBP, which value we do not really care, right? We can put garbage there, make sense? So 14 bytes plus another 4 bytes of garbage, that's 18 bytes of garbage, make sense? Now after that 18 bytes, we have 4 bytes of address, and we use the address of print secret. So there is already a function or print flag, print secret, right? We use that address. So when it returns, it will return to print flag. Okay. However, after the exploit will look like this. First of all, this one takes input from std, so we have to pipe into this, right? Not from the command line argument. So 18 bytes of garbage, the return address, pipe the whole thing into the program. So after we do this, what are we getting here? We're getting the flag. Besides getting the flag, what we're getting? We're getting a segmentation fault. But why do we get a segmentation fault?
We put junk into EBP.
Exactly. Yeah. So yeah, exactly. Because we put the garbage value put in the saved EBP, and eventually that EBP will be dereferenced. But fortunately, that's after we get the flag. So yeah. Okay, so let's go. Let's return. Return. What? So first you run this program, and the program shows you the address of print flag, right? It's this number. And no matter how many times you run this program, it always show you the same address. actually in your current laptop phone, there is a security feature called address space layout randomization, which makes sure every time you run the same program, this address space is randomized, so it will not have the same address. So on the server, for now, we disabled this security feature, to make things easier for you. So in 3-4 weeks, we are going to enable that feature, and you are going to bypass that feature. Okay. So right now, that feature is actually many ways to bypass it. It's just another layer of defense. It's sometimes it's effective, but sometimes it's just slow you down a little bit. Okay. But right now we disable that. Okay. So in this one, then I will. So do you have any questions? I think you should already understand why this works, right? Then I will give you time to work on both the 32-bit version and 64-bit version. We only look at the 32-bit version of the disassembly. We didn't look at the 64-bit version. They may have different size, also different address. Yeah, pay attention to that. Yeah. Work on the 32-bit first. Syntax, you're using double quotes there. Should be. Oh, okay. Got it. Oh, got it. You got it? Good. 32-bit? Yes. Okay. I see what the problem is, but I
see, yeah,
need,
I see it.
yeah, you see that, right? No, not that. That's not the problem. Yeah. This one takes input from std in, not command line arguments. Yeah. So I need to pipe into it. Okay, there. This syntax is correct. Okay. Oops, right track.
Yeah, I got it.
Because the dollar sign.
Yeah,
But do you understand why it doesn't work?
yeah, because that's to, like put input into an existing command, which this is a pipe, so you actually just want to print it.
Yes.
As it is.
So what that does is to run that Python code, then whatever is that will be run as a
Yeah,
run as a
like-
command, but you don't have that command. Yeah.
I was looking at how did you know this 14 was for 18
Look at the
months?
disassembly code.
So this is
Does not matter. What matters here, you see, there is a function called puts, right? This is function called put, and you know the puts, the parameter is a buffer.
Right.
From the C code.
yes.
So basically the buffer address is in EAX. Then what is in EAX? It's EBP minus E.
Oh, okay.
So you're using AT&T syntax here?
Oh, that is
You
right.
you can use the Intel syntax.
It is right.
M. You should be uppercase. But if you read AT&T, it's fine. Okay. So EBP minus E is where the buffer is. Yeah.
Okay.
So E is what? E is 14.
Yeah.
Yeah.
Did the 32-bit one.
Yeah.
Figure out the size.
64-bit.
Yeah.
It's almost the same. Yes, I would use OBJ down. I think it's also a good time if you guys want to buy Binary Ninja or other tools. Dash E, then dash M. Look at application. Intel, if you want Intel syntax, yeah. ION, PM. Yeah, and the program name. The name of the program, yeah.
Should I have done?
Just buffer content. Yep. Yep.
This is adding 17.
Why 17? One zero. No, that matters. That doesn't matter. So see, this is a call to get, right?
Yeah.
The parameter of get is the address. What's the parameter here? Parameter is in RDI. Because it's 64-bit. RDI is for RX. RX is just RBP minus 6. It's just 6.
The buffer is
The buffer is just 6. Yeah.
but then it should work.
No. First of all, hold on. This is 64-bit, right? Yeah. See how big is this address?
Or there should be zeros. And it will-
Yeah. Yeah. There should be many zeros. And also, don't forget about the save the RPP there. You're trying to override, you're trying to overwrite the return address, not the RPP. Forget about
At
that.
this point, I'm at the RVP.
Yes.
I need to add.
And you are not writing, you're only overwriting 3 bytes. The lower 3 bytes of RPP on the correct value.
And the value.
Yes.
Well,
Where are you? Oh, you're still reading code? Okay. Where are you? So you got through the. Yeah. So the reason I'm using gets instead of a string copy for this particular challenge in 64-bit is because I want you guys to input zeros, right? Because if you do string copy, you cannot input zero. Yeah. Yes, just buffer address. The address of the buffer. So here, the RDI is correct. RDI is for RX, RX is this address, RBP minus 6. Which means the buffer is actually 6 bytes.
Yeah.
That don't really matter.
Okay, yeah, then
That don't really matter.
6 plus then the
Yes.
return address is 8 bytes.
No, return address is 8 bytes, yes.
And then
But there is also a saved RBP 8 bytes. Yeah. Put in here. Which one is this? 32? Okay. Anyone got 64 bits? Got those?
Yeah.
Alright. Cool. Great. You, we're working on 32. Okay. What is 12? You have to do this work? Okay, so what is the address of flag, the print flag function? Seems you forgot about that. So you're trying to run this program, run it first,
On this, when you click on it,
just run the
gives you a
program.
box with the.
So there's some syntax error.
You
No,
need to
anything.
submit for.
Yeah, that's the, yeah. that's
I
syntax
guess so,
error.
yeah.
Okay, then you print. Then you use Python command and print. Oh,
Yeah,
yes.
I mean, that's how you put the points.
How do we
It's
download
part
the
of
files?
CTF thing. If you
Binary?
submit the flag and that's when you.
Go to the challenge. Go to the challenge.
Oh, I see.
Yeah, there is a button for you to
I'm not sure
download.
about that.
Where are the points? See,
So when you click on a challenge,
yeah. I know how to submit the flag.
you've submitted the flag, right? So it does. When you submit the flag, it gives you 1 point for that challenge. The number below that is the number of points. And so the midterm, I mean, currently has 1 point, but I guess it would be more. But when they kind of.
So here, you have a lot of A, this A is a variable. It's here, you say, this is a letter. Yes, a lot of syntax errors. Which one is?
So we're trying to run to the address. See, versus this separate.
No. Why do you get 6? How did you get 6? 6 is from.
It should be 18. 80 plus.
Should be. What's the value?
The Minecraft.
But you don't understand why it's 18.
Yeah, because you're covering.
Yeah, it's like something that's completely not there. You don't need it.
So what are you trying to?
You want to, you gotta find the vol foo function, and then you have to, the vol foo.
18, that's 18.
Yeah, it's somewhere in here, it's gonna be one of these things, so there's the main fund, there's the vol foo, and then you need to, it's just like the function that has the, phone number. It's all in it, so, and then you have to figure out. If I need the return address, so you're gonna find where the EVP is and in order to add. So then you have to figure out where the buffer is.
We are still trying to do 1, 2, 3, 4, 5, 6. That's not what we're doing here. See,
Figure out.
we're not trying to override local variable in here. There's no local variable.
Put in.
We're trying to override the return address for a particular value. And the particular value is a print flag address.
We're trying to get the flag.
See, the program address print offset for you. What's a print flag address?
If you change the return address, so if you scroll down and just run the program.
See, 18, you can call it.
If you got everything, maybe you can also help your labor.
Yeah, so that's gonna be the address of the function that we're trying to replace. So when it calls the which is the return address on the stack, we want to replace that return address with the full address. So it's kind of like, it's similar to the last problem where you have to pull up a buffer with a bunch of nonsense. And then put 6 and get that value in. And it's, that will change. So you have to figure out how many garbage values to put into the buffer in order for you to get to the
So we have 14 bytes to put. Yes. Yes.
So first is 6.
From the object.
This is equal to this.
And 6 is.
And 6 is.
So
14, 10.
it's just like another way that you can,
Three-
like, the
three
buffer
fifteen
with one
bytes
tactical
to
variable. So you have like the last example, which is for like
and I was
overriding
trying
multiple variables, and then for this is return
because
address. It's changing the return address, so like hypothetically in the way that.
I guess
This,
actually
you should have
I
it
guess we are overriding anything.
because you can change where return.
What are you overriding with this part?
The place where it returns to.
This
This is the address of the.
Yeah, so bulk function
This is 14 bytes of buffer,
Oh,
right?
yeah.
It's higher than a buffer, what is?
no, so
That's
inside
address
bulk
already.
function,
That's
if
the
you look
same
at the this code, you scroll over.
So this one is actually correct, 18 is correct.
A why?
But
So it calls.
8 is correct, because
It calls.
the buffer is 14 bytes.
Function.
The safety is a lot of
Then
bytes.
I also
You
believe
don't need the value of the
bulk
safety.
function it calls the get
That's why you
command.
move 4 bytes of garbage there as well.
The gets functions the one that
Then
allows
here
us
need
to
a
go.
return address.
Right.
The problem is the return address is
That
wrong.
allows us to change if it's like it's not done.
The thick bit buffer and then.
Yeah, it's just called get.
Let's swap that.
Let's see if we-
This is 1 byte, why did you just swap 1 byte there? It just in the onionness, not inside 1 byte.
Oh, okay.
Yeah.
So that would be.
So you're printing 1, 2, 3, 4, 5, 6. But also that's the size of just the buffer. But you need the buffer and the return address, because you need to get past both the buffer and the return address to get to. It's the same thing. Where you have
Yeah.
Right now, you're just gonna be that important.
Is calling the gets.
Every byte, just
How
because
do you get
It
like
gets-
better at knowing?
Yeah, it's just a standard C.
Part you have to like put the.
It's just because he showed us this, just if you open up the
Right.
lecture notes.
you already know where's the buffer. Then you already know the structure. The structure is always like that, right? Well, not always like that, but on our code, in most cases it's like that.
So this is the alter
There is a save the EBB.
and the notch, and this is the
There
gets
is return
function,
address on top.
and it gets input from standard.
And you need to decide, you are trying to override save the EBP, or you are trying to override the return address. Today, we're only overriding the return address. Save the EBP. Next week, we're overriding.
So-
save the EBP.
Stack, variables, so you have
I don't know
So
how,
just.
what exactly is.
Then you.
But basically you treat the object off and then.
Exactly.
Draw the stack.
Even everything is part of the code.
So we're
When
trying
you
to.
code, you understand what's going on.
We allocated
Yeah.
a buffer.
And binary
And
is
it gets
very
functional allows to
Binary
go
job also give you the
out of bounds of that
disassembly.
buffer.
It can also give you pseudo C
Put
code.
enough into.
When the program gets very
Go
complicated,
out of bounds,
because
then you
pseudo
have
C
to
code
return address.
to understand.
But it doesn't give us.
And then you can change it.
No. It's on the, it's in the code.
It's just like an array.
Try to understand the problem.
Just like an
Like
array.
you to staking.
We allocate a buffer with length 6, so it's 6 bytes. And it can go up like. You can go up as much as you want. Eventually, you're gonna get a segmentation fault, but you keep going up. But at a certain level of, there's like a certain byte that you're at, it'll allow you to get, to change the return address. It's just when you go outside of like the memory that the program allows you to access.
But I was pointing to the middle of it. So this whole thing is something 18 bytes.
That's gonna be Intel syntax.
But the buffer is actually.
So it's OBJ, so if you want to do the OBJ down.
Not at, the buffer is not at EBP minus 18.
Yeah, so then what you wanna do is, in the previous example, yes, the Python 2, but you said this time you want.
This is proof, right?
It is.
Proof takes one parameter, which is average.
Executable because the gets function.
And the answer is buffer is push down to stack.
So you wanna
Yeah.
do like Python two.
Yeah.
And then you wanna put it into the buffer, you can actually collect it. Here's what you do, I just standard in. And then it will,
Exactly.
We overrode it with that.
and then you pipe, so then you pipe, and then you just run it.
Yes.
And then it will take what you put into that shell command and put it, and use it as standard in for the get solutions.
Are not able to stack.
What are these security features?
So that you just have to the buffer, because there's not.
Yeah, 6+8.
Yeah, so you can change the return address and have it run a function that has malicious, and so like think about like if there's.
It's how easy is that, is like.
Well, I mean, nowadays, it's, I imagine very difficult to do this, but.
Yeah, I bet there is, I was thinking to this.
Okay.
Well, yes, it's gonna be in the health reduction.
L3.
Yeah, I don't think this is a D6.
It's like the.
Oh, is that, so it's just interpreting it.
The umlaut O thing.
It's gonna be something along these.
Oh, that's weird.
Two, to a degree.
So you need to 32, an example, right?
That's what we subtracted this.
14 from 32.
Python two and on three are printing different things. I was trying to.
So-
Could it be because of the
The puts function.
The dash C is just to without the function or to directly emphasize like.
STP is the.
Yeah.
The
standard
function will do that, but apparently here it's actually on stack, so who put that on stack from where? From ES.
Standard, like, they're both fine, printing standard in, and just like they print that.
So I know.
Yeah, it's how.
E is 14.
Yes.
So you can have those like the what is on top of E, you can
Standard in.
whatever E, like it points to.
Function, so like you would try to run something with.
All lines. And you call it.
Yes.
So you call
Flash,
it.
the executable name.
Right.
But it's the tool version,
It's just
64.
exactly, it's just that E
I did, okay,
Here,
here's my calculation.
we have 65 here. We're subtracting.
Yes.
6.
It's over 6. I don't know what happened is, and then, it's on
You have.
R, which is 8 bytes,
things, right?
Yes.
right?
Which means the buffer
And
is
then
only
if
6
you
bytes.
execute this program, you only get.
Okay, what is the size of the same EVP?
So you have to pad it.
64 bits.
Yes.
Bits, which is 8 bytes.
Yes.
6 bytes plus 8
Why did
bytes
it do
is 14.
I did, it's heading 1, 2, 3. And then I put one more because it's a 0.
Both? Okay, cool. Yeah, if you got both, you can also start working on the homework. There are several challenges I didn't cover in the class.
Because you have to have the pad.
Which way is the
Well, I think it's all.
So this is a low. This is high. So when you write something, copy something, you copy from low parameter just high end.
Because it shows you, so when you.
Yes.
Yeah.
Yes.
That's why I love my series.
Sometimes the compiler gives you six,
Yes.
so you just gotta make sure that it really gives you six. So when it says, oh, it's six.
Yeah.
Into it.
No. I believe it's gonna be this. Yeah, it's gonna be the week.
Oh.
It's not 64, it's gonna be-
I got 64 on this one, I'm doing the.
Oh, yeah.
Yeah.
Oh, you return two.
Yeah.
I see,
So,
okay.
when it pushes, it's gonna.
The only thing I don't understand is, never turn two.
Oh, this one.
Yeah.
Return two, maybe you can do it next week. This is much more complicated. Yeah.
Okay. I did the return two for 32 bit,
Right now, this instance of EVP is the same value as ESP.
so the one above.
And then
This one.
it subtracts it twice,
Oh, you did this one. We are trying to do 64 bits.
Yeah.
Oh, okay.
What I don't understand is like, this thing does not matter. So it could be any length.
No, the value doesn't matter. The size is also 4 bytes.
Oh,
Yeah.
I see.
So-
But in the 64 one would be feet, right?
No, 64 bits doesn't work this way. Only after we learn return oriented programming is the next.
I see.
No, not next the class. After midterm, we will know how to do that.
Okay.
Not right now.
Okay.
Right now you don't know this. You know why?
This is.
Because here you are overwriting a parameter.
That's just like.
Stack, right?
Yeah.
To make sure it's stacked. But in 64 bits, the parameter is not on stack, it's on register.
And now we.
That's why here you are only overriding stack.
Now we know.
You cannot change the register. You don't have an approach to do that.
So now you wanna go. Now change the form of it.
Yes.
The buffer parameters will override, but on 64-bit,
You need to use another approach to change the register.
Yeah, because 14
it makes sense.
Yes.
make the array go all the way up to.
So this is not in the homework today, so.
And then.
I just thought it went like
Add 4 more
return
lines
one,
on.
return two, I was like.
Yeah.
That is the return address you want to change.
It's a good textbook. for
Oh,
lots of-
Oh, this is-
So sure, I'm not gonna read it. Read it multiple times.
Yes, so that's the old
Yeah.
stack.
You got everything or?
I got the 32 one. I'm
Still
good.
got 64.
Yeah.
Oh, you
But I'm trying to do
It's
this
return
by myself, so I
So when
can.
we go, so when we try to return from a function. It pops everything off the stack, it's gonna change the middle stack pointer to that new base pointer, and it's gonna go up one to that return address. And set the program counter to that return address, and then it's gonna kick over to
This
that,
is semester homework?
where that is.
This is last semester. Can you go back?
So we want
Can you
to
go to my website?
change that return address. Because if we change the return address, it's going to return to a different function, a different location than it was supposed to.
That's
This way
different.
to when I was
Oh.
doing the kind with the key address.
Yeah, I did like all the theories, providing theories to get it to remember this.
Or you put like 4 bytes in, or I'll put 1 byte of
Any questions?
0.
Oh, really?
It accepted it. Oh, I think it might be because the
Yeah.
like the
Yes, that's 14.
since it's little endian, like it automatically has zeros on them.
The padding.
Yeah, or not the padding necessarily, but. Or it might be referred to as that, but it's like if it's like zeros.
That's the same thing. So this is a stack, like you said, this is stack, right? Which means this is memory. This is memory. But EBP is a register.
That is like the area for the buffer, right? And the buffer is actually just
EBP, in your program, points to the save EBP.
Yeah, 6 bytes.
Why it points to the save EBP? Because at the beginning, you can push
And that's why it's like
the
the.
EBP point, the EBP points to the
Print one.
Yeah.
Flyers.
That makes sense.
Yeah.
It's clear.
Somewhere here, so because EBP points to here, the EBP minus E will be somewhere here. And this size. Here. Yes. Here, exactly. Yeah. Yes, returns on top of that, yeah. Yes, change the value of the return, yeah, basically. The value, the semantic meaning of the value is we change the value, yeah.
In terms of like filling this part.
Yes.
By trash.
Yeah. Yeah. And fail it with anything. Maybe anything.
So basically, it's readable based on. So now
Yes.
RSP and RPP. So like this location is like RSP and RPP are same place.
And then it should be times.
So point
Yes. Yes. That's just analysis.
Okay, see,
Yes.
visualize this.
That's right.
This is previous RPP. Input by RPP. This is where RSP is pointed.
No,
right?
Okay.
And
So
so we are moving RSP,
got
with the value RSP is pointing into RPP register.
And since this is overflow local, which means we're trying to just override data. So the base going to initially be for the main function. We just have to override. Say,
Other function, yeah, and then it's going here.
So it's like. So there's also reading function that's pushing it on this. After
Yeah,
that,
I see. The model really
what the new function to get this hat.
New function to get
Oh, this
the
is-
weight. Yeah, exactly, so,
you're changing the starting point.
yeah, so basically, so, you know, it's this is what's happening, both will be coming into.
I was just,
Right, and then you're subtracting, I mean, so you're adding 10 bytes. So 10 bytes, then RSP will be pointing to
Upload.
byte
yeah, go to
after
challenge.
10. So basically, it's
Go to
RDP
challenge. Yeah.
minus 10.
Go to that challenge.
So that will be RSP. So
Download.
RAX,
Yeah.
so here
You can upload that to.
we are holding the effective address. That is RPP 6. And here. So 4 is empty.
Yeah, it didn't put it,
We are
you didn't
not-
put the address. You did not override the address, you only fill the buffer,
Yeah.
see?
So this is the filling the buffer.
Yes, fill in the buffer and save the EVP, but then you need to put the address there.
But I'm always saving the.
You do not save the, you only overflow. Yeah, we need to put this address. This after this, yeah.
9, 8,
So where are you?
I was just exploring Python 3, it's just Python 2.
Yeah, it's a different syntax, you use all those, yeah.
It's like Python 2 uses ASCII and Python 3 uses, Unicode.
Yes, exactly, so if we want to generate the same raw bytes with Python 3, it will be much longer.
16.
Yeah, that makes sense, because I was trying to go with like,
RPP
Python
is
3 could
10 bytes
just
after.
strings.
Exactly. No, you use the same approach before, you need to put byte by byte of that address. Use the same approach as the previous. Change. Which one is this? 64. Okay. Okay. Yes. Yes, it's the same idea as the 32-bit. Well, there are many errors. First,
Like, mail it to the website.
size.
You download the
Size
file.
is not correct.
I have to do.
Size is not.
No, it's on the
correct.
cloud, that's what.
First, the size is not correct because there is 6, right? So how did you get 10? 6 plus 4? It's not 4, it's 8. Yeah, the second, that address is not 3 bytes, it should be 8 bytes. You are saying 3 bytes because there are zeros. Yeah. It's not 8, it should be 6 plus 8, 14. For the homework overflow 3, I think you can use binary ninja to get a high level idea because that overflow function is a little bit bigger than what you saw in the class. So you can use binary ninja to get a decompiled C version to get a rough idea what that piece of program is doing first. Just got it right. Syntax error. Yeah. You need to start from beginning. in a new one, yeah. Just the type under. Control shift meters. Yeah, okay. Yeah, you need to change this. You have two Pythons, two there saying. You have Python 2, Python 2, you have two commands.
Why do I have to come in?
You need to, you have two lines of those commands.
Why this is happening?
Just be slide.
Sorry, can you return it?
56, so which 32-bit version? It's not 14, it should be 18.
It's 18.
Yeah, 18, because E is 14, then you need to also override the save the EBP, which is another 4 bytes, so it's 18. Yeah, 14 plus
Yes.
4.
So it's 16.
Yeah.
Okay. So why this is negation?
I guess segmentation for it because, sorry. I think because gets were add 2 bytes at the end, and that 2 bytes were, oh, well, because you override the save the EBP. You put the graph in the save the EBP, so you can really get segmentation for it. Yeah. Yeah, because the save the EBP, this one, this value is also important.
Where did I put them?
That 18. That 18 has 4 bytes, goes to here. A.
Can I fix this?
No, right now. Yeah. That really matter for the mark.
Oh, no.
Your goal is to get the flag.
Okay.
It's not to
Yeah.
by process. You don't have to, but no, just use a cloud version.
Oh,
It's free, yeah. Yeah, it's much easier, cloud version.
Yes, what is different?
64 to 1. Yeah, okay, I guess we can stop there here today. So next class, we'll talk about how to overflow return address to multiple functions. We are going to chain functions together. We are also going to return to functions with parameters. But that one we will only do 32-bit because for 64-bit, the parameters are not on stack, they are in registers. So right now, we only have the ability to override the stack. We don't have the ability to change registers yet. So only after the midterm, after we learn return oriented programming, we will learn how we can change registers. Okay, so 64-bit will lead to the second half of the class. So let me explain a little bit about the homework. So this week's homework, there are many challenges. So start early. The beginning is simple. The first several ones are simple. I think the overflow 3, 4, 5, maybe at least 2 of them may be a little bit challenging. 3, the vol function is more, it's quite complicated. So I suggest use binary ninja to decompile to say. So the idea is using the decompile say you can understand what the program is doing, but you do not get the actual address. You do not get the actual offset. When you hack, you really need those. Those you need to get from the binary code. 4, 5, I remember they are simpler. 4 was supposed to be hard, but the compiler optimized it away. Then I didn't bother to change, so it's actually not as difficult. 5 is also not difficult. So whenever you have questions, just ping me on Slack. We can meet anytime. So
Just send you a message on the Slack.
yeah, just ping me on Slack. And also the TA will also be there.
And your office hours is right before this.
My office hour is before the class, but like I said, if you want to meet, just ping me. Then we schedule another time. Yeah, that will be much more convenient. because my office is not really on campus. Our campus, our building is next to Prudential's. It's like
Oh, yeah, that is.
half miles away. Yeah, online is much easier. Okay, see you guys next week. Not necessarily.
That is
Yeah.
like the nine.
So supposed to be 9:20.
Okay, great.
I feel everyone's tired. I don't want to.
We're gonna try to go something.
You guys are.